Hello, everyone. Good morning. This is Chris Scotese. Today I'll be talking about some recent plate tectonic reconstructions I've made for the Mesoproterozoic, the Neoproterozoic, and the early Paleozoic. I'd like to thank Dr. Jillian Hay for the invitation to give this talk. And I'd like to give a quick shout out to my comrade, Professor Zhengjiang Li, who by far and away is the most outstanding plate tectonic modeler in China. If you have any questions about my talk, he would be a good person to talk to after my presentation. This summarizes what I'll be talking about. Sort of a lot to go over, but fairly simple. It's a formation and breakup of supercontinents during the middle and late Paleozoic. The three continents we're talking about are Nuna, Rodinia, Pannotia, and I'm adding a fourth continent to the scheme called Terra Borealis. Anyway, the sequence of events is the breakup of Nuna, the assembly of this new continent, Terra Borealis, about 1,200 million years ago, the breakup of Terra Borealis and the formation of the Paleopanthelastic Ocean, the familiar assembly of Rodinia at about 1 billion years, the breakup of Rodinia 250 million years later, the formation of Pannotia, followed by its quick breakup, and the breakup led to the opening of the Iapetus Ocean and a series of other back arc basins. Another important event that we'll be talking about is the formation of a subduction zone in the middle of Iapetus Ocean that eventually led to the collision of the tectonic arc. It's very difficult to make Precambrian plate tectonic reconstructions. That's because we have very little data, and we're restricted to studying things like continental tectonics. Paleomagnetism is probably the most important single data set. Sometimes you can use paleoclimatic evidence like tillites. There may have been episodes of true polar wander during the Precambrian. So without a lot of evidence, we have to rely on what I call plate tectonic rules, which are a way of using educated guesses to tell the story. The methodology is actually fairly simple. We define the plates, or define the tectonic elements, the things that are moving around. By looking at the tectonic history along the margins of these tectonic elements, we can deduce times of rifting and collision. We orient the tectonic elements using paleomagnetic data. And in this regard, we put together a new database of over 17,000 paleopoles, which is a compilation of more than half a dozen other syntheses. The tricky part comes in estimating the longitudinal separation based on the history of rifting and collision. And what you try to do is the motions of the plates have to be reasonable. They have to represent rates similar to the modern world, so that for slow-moving plates, 3 centimeters a year, fast-moving plates, about 10 centimeters a year. Once we have the motions and the plate boundaries, we then can even estimate the age of the ocean floor, which is, again, is very speculative. So this is a map of the various bits and pieces, what I call tectonic elements, what some other groups call geodynamic units. But anyway, the point is these are all the bits that have moved independently at some point in time. As I mentioned, the Paleomagnetic pole compilation is based on the synthesis of numerous workers. So we're not trying to look at the best poles per se. We're trying to look at all the poles and see what patterns we can come up with. For these reconstructions, about 5,000 paleomagnetic poles were used. The database is very simple. There's only about 20 or so fields, but they're the type of information you need to make plate tectonic reconstructions. Obviously, the pole position, uh, some estimate of quality, age range, etc. And this is how I portray the paleomagnetic poles. Again, it's a little bit different than what most people do. Each pole is represented by the colored dot, and the color of the dot represents the continent or tectonic element the pole is from. So what you want to see in any reconstruction is a good mix of different colors represents data from different continents. Each pole is encircled by its alpha 95, and which I've indicated by this light shading of gray. And the obvious thing is that if the poles cluster, the alpha 95s overlap, and you get a more dense, more white representation. So at 750, we see that there's a good cluster of poles that's centered on the north spin axis. Now, because we have so little evidence, what we really need to do is invoke some laws or rules of thumb or observations. And I'm calling this sort of metaplate tectonics. Basically, it's the study of the interaction of evolving plate boundaries. So plates don't just move. There are catastrophic events like plate continental collisions or subduction of mid-ocean ridges. And these catastrophic events punctuate periods of long normal plate motion. As these catastrophic events which change the motion of plates and create new ocean basins and continents. I won't go through what I call the rules of plate tectonics. Most of them are fairly obvious. Things like subduction is the principal driving force, and the mantle plumes are important because they provide zones of weakness, but they don't in themselves drive the plates. The last rule is probably the most important. Plate tectonics is a catastrophic system, not a chaotic system. Catastrophic system. That means that every once in a while there's a major event, wham, as a plate tectonic situation, the whole dynamics change. Okay, what's new about this presentation is the Terra Borealis. In the late Precambrian, we have Nuna assembling about 1800 and Rodinia at 1000. 800 million years is too long for nothing else to happen, so Terra Borealis sort of fits in between. What makes it unusual is it assembled at the North Pole. The core was East Gondwana, which had just assembled, and brought together the remnants of Nuna. So again, the key is East Gondwana. What you should notice on this diagram are the blue and the green lines. The blue lines are the Pan-African sutures between Africa and East Gondwana. This is essentially the major Pan-African suture that assembled Gondwana, but East Gondwana assembled when these sutures in green collided, bringing together bits and pieces of Nuna. This is a quick look at the North Pole at the time of the assembly of Terra Borealis. And it's kind of confusing, but to help you get your eye in, this is Australia. And you can see Australia was originally at least three pieces. A Northern Australian piece, a Western Australian piece that included Northern India, and a Southern piece that included parts of Antarctica. So these three sutures closed about 1200 million years ago. Possibly a few other sutures closed. That gave us Terra Borealis. 70 million years later, Terra Borealis began to break apart, and this is what I'll be showing you in more detail. Don't bother looking at this. It's the same diagram, just rotated. This is the cluster of poles at 1200, so it's a pretty good fit to the paleomagnetic data. Now, Terra Borealis fits into to the history of plate motions, which I like to illustrate using this, what I call a phyllotectonic tree. Each branch is a rift, each rootlet joining is a collision. If we go back in time, we see Pangaea, and the Pangaea was put together by Paleozoic collisions. And then in the late Precambrian, we have the three supercontinents, Pannotia, Rodinia, Terra Borealis, and then Nuna. And then what happened prior to Nuna is very conjectural, very speculative, but I envision it as a lot of little pieces finally getting together, forming continental nuclei, and eventually becoming larger and larger. But leading up to the formation of Rodinia, we have one very significant event, and that's the collision of Amazonia with Laurentia, closing this ocean and forming the Grenville event. As I mentioned, Terra Borealis began to break apart about 1100 million years ago. Here we see the rift represented as a triple junction, and the triple junction expands and eventually becomes the Proto-Panthelastic Ocean. So bits of Siberia and Baltica swing westward, the Congo Craton swings eastward, being pulled towards the remnants of Terra Borealis by the subduction zones on either side. This is a cluster of the paleopoles at 1,000. And this is just looking at it from an orthographic point of view. Initially very slow spreading, and then rapid expansion. So 1,000 million years ago, we have a Pangaean world with an ocean on one side, with the Panthelastic spreading center, and a supercontinent on the other side. Minor adjustment between 1,000 and 900 is a rotation of Baltica, closing against Laurentia and Amazonia, opening the Aegean Sea. So we formed Rodinia 1,000 million years ago. Why did Rodinia break apart? My hypothesis, again having to do with metaplate tectonics, is that this spreading center eventually migrated closer and closer to the subduction zone, and at about 760 was completely subducted. Again, cluster poles for 800, 750. So what happens when an ocean doesn't have a spreading center anymore? Well, either a new rift will form in the ocean basin, or the supercontinent will rift apart, being pulled essentially apart by the slab pull forces. And so that's, in my model, what happens to Rodinia is at about 750, a new spreading center begins in the Panthelastic Ocean, and it opens up, and as a consequence, the southern half of Rodinia goes over the South Pole to get glaciated in the snowball Earth, and the northern half of Rodinia goes over the North Pole. And we have the Sinian Tillites in China, for example. Here's a cluster of poles at 600 million years. So again, this just tells the story of what happened to those. So we've broken up Rodinia. We're now going to form Pannotia and open up the Iapetus Ocean. And that's what's represented in this diagram. We have basically a supercontinent, new supercontinent, Pannotia. Here's the rift that split Rodinia. By 560, Laurentia and Siberia begin to rift away, opening up two branches of the Iapetus Ocean, a southwest and a central. At about the same time, a back arc basin opens adjacent to western Siberia, and this is the Kipchak Arc. And these are all the chunks of Kazakhstan. This ocean continues to widen through the Cambrian. So the major events in the Cambrian are the opening of Iapetus and rifting of Avalonia, opening of a Uralian back arc basin, and then significantly the Proto-Tethyan mid-ocean ridge is subducted beneath the Kipchak Arc about 510 million years ago. So a lot is happening about 500 million years ago. Here's a cluster of the poles for various times, 541, 530, 500. I've highlighted on this diagram all the poles circled are from North America, so you can see in general the North American data is centered at the pole, but it's very dispersed. So here's the events during the Cambrian, the widening of the Iapetus Ocean. An interesting event happens at 505. A new subduction zone starts in the middle of the ocean, which subducts the western half of Iapetus and rifts Avalonia away, and this arc eventually collides with North America, forming the Tectonic arc. So again, 560, 540, 520, 510. Interesting, we see the subduction of this ridge. That results in a jump of the ridge and the separation of what's called the Precordillera Cunha terrain. We have the arc, which cuts across old rifting boundaries, and eventually that arc moves and collides with North America and Laurentia. Here's the story of the Proto-Tethys. Again, another good example of metaplate tectonics. Proto-Tethys is ocean floor being subducted beneath the bits of central Kazakhstan. Here's the back arc basin, Kipchak back arc basin. And so what we see is at 520, this ridge is approaching the trench. It's subducted at 500, which means this ocean floor is being pulled into the trench, and that rifts away the Carthasian pieces, South China and North China, by the late Ordovician. So the late Ordovician is just a completion of some of these trends. Again, the Paleomagnetic clustering of the poles. And since my time is running out, I won't say a lot about this other than these subduction zones eventually consume the ocean floor, separating Laurentia, Baltica, and Siberia as we form sort of the nucleus of what's going to become Pangaea. So Avalonia rifts away, the Tectonic arc collides, and then we put it all together. And this summarizes everything, but also in yellow, the points I'm making is that things happen for a reason, and the reason is either subduction of ridges or the collisions of continents which destroy subduction zones. And so we have to look at plate tectonics as an evolving process, not as a simple static dynamic things happening in sort of a continuous fashion. What's important are the triggers, are the metastable events which change global plate stresses. So I'll stop here and thank you for your attention.